You probably think of helium as, the party trick gas, the stuff that makes your voice squeaky and keeps balloons floating.
Right, the fun stuff.
But here's something that might really make you think. The tech you're using right this second, your phone, your laptop, it absolutely depends on that same gas.
It's kind of mind-blowing, isn't it, how essential it is?
Yeah. So today we're doing a deep dive, actually sparked by an article from Sabine Hossenfelder called "We're Running Out of Helium, but There's Hope." We want to unpack this critical situation, and maybe a surprising bit of good news.
And it's interesting because the sources we both looked at, they show this real concern about resource scarcity, especially for things we don't always think about. Helium's a perfect example.
Exactly. So
Right.
our mission today basically is to figure out why helium is so important, what's really going on with these shortages, and what about this new scientific discovery? What could that actually mean?
Let's get into it.
Okay, so first things first. Why are we even worried about running out? I mean, it can't just be party balloons causing a global shortage.
Sure. No, definitely not. The fundamental problem, like the article lays out, is that helium is just incredibly light. Its atomic weight is super low.
Okay.
So once it gets into the atmosphere, and it leaks out pretty easily from, wherever it's stored or used,
Yeah.
it's just so light it literally floats away, off into space,
Gone for good.
gone for good. We can't really recapture it from the atmosphere in any practical way. So the helium we have trapped underground, that's pretty much all we're going to get from Earth itself. It's non-renewable in that sense.
Wow. And this isn't exactly a new fear, is it? The article mentioned we've hit shortages before.
That's right. This isn't the first time. We've actually seen 4 major helium shortages over the years.
4. Okay.
Okay. The latest one only really started easing up in early 2024. That one was mostly triggered by some big production facility outages, key plants in the U.S., and also Qatar had problems.
Right. I think I remember hearing about issues in Qatar. They're a huge producer, aren't they?
Absolutely huge. And when facilities like that go offline, it shows just how, well, fragile the supply chain can be, even for something like helium.
And these shortages aren't just theoretical, are they? They hit actual industries. The article specifically called out one major sector.
It did. The semiconductor industry. They really feel these shortages quickly.
And that's huge because chips are in everything now.
Everything, your phone, your computer, cars, medical equipment. I mean, the list is endless. So a helium shortage can have these massive ripple effects across the whole economy, across our daily lives.
It really is kind of an unsung hero of the modern world then, without it.
Things would look very different. The tech we rely on just wouldn't work the same way, or might not even exist in its current form.
Okay, so beyond the balloons and the funny voices, let's dig into why it's so critical for tech. Why should our listeners really care about this?
Right, let's put the balloons aside. Helium's role in high-tech manufacturing is indispensable. Take microchip production. It's used in several absolutely vital steps.
Like what?
Well, there's plasma etching. You can sort of picture it like a microscopic sandblaster, using plasma energized with helium to carve incredibly precise patterns onto silicon wafers.
Okay, etching.
And then there's extreme ultraviolet lithography, EUV. That's another crucial process for making the most advanced chips. It uses a very specific wavelength of light, and helium helps create the right environment for that process. It's about printing tinier and tinier circuits.
Wow. So it's involved in the actual making of the chip patterns, but it's also about temperature, isn't it? Keeping things cool.
Exactly. Helium is fantastic at transferring heat. It has incredibly high thermal conductivity. Plus, and this is key, it's chemically inert.
Meaning it doesn't react with stuff.
Precisely. It won't corrode or interfere with the delicate materials used in these high-tech processes or equipment. So you combine great heat transfer with being totally non-reactive, and you get the perfect coolant for some really sensitive applications.
What kind of applications need that level of cooling?
Well, chip manufacturing itself needs precise temperature control. But also think about MRI machines in hospitals. They rely on superconducting magnets.
Right, the big donut things.
Yeah. And those magnets need to be kept incredibly cold, using liquid helium. Same goes for giant particle accelerators, like the ones at CERN, pushing the boundaries of physics.
And then quantum computers, too, I read.
Yes, absolutely.
Yeah.
Quantum computing is a huge emerging field, and the qubits, the basic building blocks, often need to operate at temperatures just fractions of a degree above absolute zero. Liquid helium is essential for that.
That boiling point you mentioned earlier, 4.2 Kelvin, that's incredibly cold. Like minus 269 degrees Celsius, right?
That's right. Almost as cold as it can possibly get. And another weird, useful property is that it doesn't freeze solid at normal atmospheric pressure no matter how cold you get it. only under pressure.
That's bizarre, but useful, I guess.
Very useful. That whole combination, super low boiling point, high thermal conductivity, inertness, not freezing easily, it makes helium pretty much unique and irreplaceable for these very specific, very demanding jobs.
Okay, so no easy substitutes then.
Not really. Not for these ultra-low temperature applications anyway.
So we've got this vital gas that keeps floating away, and demand is, well, it sounds like it's increasing.
Dramatically. The article highlights this clearly. Global demand is growing fast, and a huge part of that is driven by, you guessed it, AI and the continued expansion of the semiconductor industry.
The very things driving future tech.
Exactly. Fields that many of our listeners are probably deeply interested in. And this demand surge is putting serious pressure on prices. The article mentioned a 5-fold increase.
5 times?
Yep, over the last 20 years or so. That really shows the economic strain.
Wow. So what about the supply side? How much do we actually think we have left in the ground?
Current estimates, and these are always a bit fuzzy, suggest maybe 50 to 70 billion cubic meters in known recoverable reserves.
Okay. And where is most of it?
Geographically, it's pretty concentrated. The big players are Qatar, Russia, and the U.S. They hold the majority of the world's known reserves.
And how do we even get it? Does it just bubble up?
Not exactly. It's usually found trapped alongside natural gas deposits within certain types of porous rock formations. So helium extraction is often linked directly to natural gas production. You extract the natural gas, and then you separate the helium out.
Ah, okay. So 50, 70 billion cubic meters. How long would that last us?
Well, at the current rate of consumption, the article suggests maybe 200 to 300 years.
Oh, that sounds okay.
It sounds okay, but here's the big but. That calculation is based on current demand, and as we just discussed, demand is rising rapidly.
Right. AI, chips.
Exactly. So
Right.
that 200, 300-year window could shrink, possibly quite significantly, depending on how fast technology evolves and how much more helium we need.
Okay, so that brings us back to the potentially worrying picture. But the article's title promised hope, this new scientific discovery you mentioned.
Yes, this is where things get really interesting and, frankly, quite unexpected.
So what was the old thinking about helium and rocks?
For a long time, the standard scientific view was that helium, because it's a noble gas, very inert, doesn't really form chemical bonds with minerals. It was thought to just get physically trapped in pockets or porous rock waiting to escape.
Okay, makes sense. It's standoffish.
Pretty much. But this new research, coming from teams in Japan and Taiwan, seems to flip that idea on its head.
Oh, so.
They ran experiments simulating the conditions deep inside the Earth. We're talking incredibly high pressures and temperatures like you'd find near the planet's core.
Right, extreme conditions.
And under those conditions, they found something surprising. Certain iron-rich minerals can actually bind with helium,
Yeah.
form a sort of chemical association.
Really? That changes things. How much helium are we talking about?
Their lab simulations suggested the binding capacity could be, get this, 5,000 times higher than anyone expected under those conditions.
5,000 times. That's huge.
It's a massive difference. And the implication is profound. It suggests that Earth might be holding on to vast quantities of helium deep underground, especially within the iron-rich core itself.
So like a hidden stash.
Sort of. A potentially enormous hidden stash that we didn't really know could exist in that form. It really makes you wonder what else might be down there, interacting in ways we haven't predicted.
Okay, but does this mean we need to like drill down to the Earth's core?
Yeah.
Because that sounds impossible.
No, thankfully not. The article makes that clear. Direct core drilling isn't feasible, or what this implies.
Okay, so what does it imply?
The idea is more subtle. It suggests that this deep-bound helium isn't necessarily stuck there forever. Over very long geological timescales, it could slowly migrate upwards, essentially replenishing the shallower helium reserves that we currently tap into.
Ah, so like a slow release mechanism, a deep reservoir feeding the upper levels.
Exactly. Think of the core, or at least these deep layers, as a slow-dripping source that adds helium back into the crusted mantle over millions of years.
Is there any real-world evidence for this? Beyond the lab simulations?
There is some intriguing supporting evidence. The article mentions studies of lava samples from Baffin Island up in Canada. These lava samples, which come from deep within the Earth, were found to have surprisingly high concentrations of helium-3, a specific isotope often associated with deep mantle sources, much higher than expected.
So that suggests helium is coming up from deep down.
It strongly suggests that, yes. It lends weight to this idea that there's a significant deep Earth helium cycle happening. And the overall conclusion, it could mean that Earth's total helium leakage into space is actually slower than we previously thought.
Which would mean the helium we have might last longer.
Potentially, yes. It offers a more optimistic long-term outlook for the planet's total helium inventory.
Okay, that is hopeful. What about making helium ourselves? I think the article touched on nuclear fusion. Could that be a solution?
Well, it's true that nuclear fusion reactions, the kind that power the sun, do produce helium as a byproduct, specifically helium-4.
Right, so could future fusion reactors solve the shortage?
There are a couple of big hurdles. First, as the article notes, we don't have commercially viable, energy-positive fusion reactors yet. We're still very much in the research and development phase. It's likely decades away, at best. Okay, so it's not an immediate fix, not at all. And second, even if we did get fusion power plants up and running globally, the amount of helium they'd produce as a byproduct would likely be relatively small compared to the massive industrial demand we have.
So it wouldn't be enough to, say, supply all the MRI machines and chip factories.
Probably not. It might contribute a little bit, but it's unlikely to be the main source. So this really underlines why understanding and managing our natural reserves and this potential deep Earth replenishment remains so important.
Got it. Fusion isn't the silver bullet here. So back to the present. Given the current pressures and the time it takes for any deep Earth helium to migrate up, what can we actually do right now?
That's the key question for the short to medium term. The article mentions some practical steps. A really important one is developing and using closed-loop helium systems much more widely.
Closed loop, meaning recycling it.
Exactly. Systems designed to capture the helium used in a process, say cooling an MRI magnet or in chip manufacturing, purify it, and then reuse it instead of just venting it into the atmosphere where it escapes.
That makes a ton of sense. Prevent the waste in the first place.
Precisely. Especially in industries that use large volumes, improving recycling and efficiency can make a huge difference in stretching the supply we have.
Is there anything, on an individual level? We talked about balloons earlier.
Yeah, and while industrial uses dwarf things like party balloons, the article does subtly make the point about being mindful of waste. Even small-scale uses add up, and just being aware that helium is a finite, valuable resource is maybe the first step. Avoiding unnecessary uses, even seemingly trivial ones, contributes to that awareness.
Right. Every little bit helps, or at least helps shift perspective.
It does.
Okay, so wrapping this up. It sounds like this discovery about helium binding deep within the Earth isn't some instant fix for current shortages.
No, definitely not an immediate solution.
But it does offer this really crucial, maybe long-term hope.
I like that analogy. The article hinted at the Earth's core acting like a slow-dripping reservoir.
It's a good way to visualize it. It suggests a natural replenishment process we weren't fully accounting for, but, and it's a big but, it doesn't change the immediate need.
We still need to be smarter about how we use it now.
Absolutely. We need continued innovation in recycling, more efficient technologies that perhaps use less helium, and just generally smarter management of this really unique and precious element.
This whole conversation really makes you think, though. If the deep Earth can hold on to helium in ways we didn't expect, what other resources might be down there? Or interacting in surprising ways?
It's a fascinating question. It really underscores how much we still don't know about our own planet's deep interior, and how geology can directly impact resource availability for technologies that seem totally unrelated, like quantum computing.
That connection between deep Earth science and cutting-edge tech, it's pretty amazing.
Well, thanks for walking through this with me. That was genuinely mind-bending stuff.
It really is fascinating. Glad we could dive into it.
And hey, if you, the listener, found this interesting and want to explore more science topics, Sabine Hossenfelder, whose article got us started, actually offers science courses. I think they're on platforms like brilliant.org, just throwing that out there if you're curious to learn more.